Well, today I want to introduce you to give you an intuitive definition of what derivatives are. I want you to take a moment to just think about them. If you have been exposed to derivatives before, and kind of think of your own definitions as we go through. Just take a moment and pause and think about it. Have you thought about it? All right. So, as a way to sort of introduce this, we need to be able to discuss whether it's really our first task is a rather straightforward one, but it's essential, is to decide what we really mean by tangent. And if we take a quick trip back to plane geometry, in geometry, things are delightfully clear cut, right? If you consider, for example, a circle that has any point P, it's sitting happily on the circumference, the point is sitting happily on the circumference of the circle, and there's always existing a unique line L that passes through the point, and it doesn't poke it actually without poking through the circle at any other point, and that's called the tangent line. The tangent line, I love, it's a model of restraint. It's never oversteps its bounds, and we sure know we could use that in America these days, right? A lot of people don't stay in their lane. A lot of lack of restraint in our modern, postmodern, I should say, societies. So, on the other hand, though, you have the secants, and that is if you take any other line through P, it's bound to cut through the circle at least one more time. And those lines, they're aggressive, they're overzealous, and they're called the secant lines. So we're going to take this idea of the tangent line and sort of tentatively adopt adopt it as our working definition when we talk about the tangent to the graph of a function. There's a clean, simple, and effective way to start understanding derivatives. Now, if you have not reviewed functions yet, I strongly urge you to instead brush up on your functions because otherwise this won't make sense. So, calculus provides the answers, and we have two natural geometric questions when we're talking about the graph of y equals f of x, right? The graph of a function. So I put here, hopefully you can see the screen. There are two questions here. Given a real number, very important that we always define the domain, the set that we're working with. When you have a real number in the domain of a function, what is the slope of the line that is tangent to the graph y equals f of x at the point a f of a? And then the question number two, right? So we just talked about what the tangent line was. And then we have question number two here. Given real numbers, and a can be less than or equal to b, such that the interval ab is a subset of the domain of a function. That's why I'm telling you to review functions. If this is not making sense, definitely review. You need to have that as a prerequisite. Any serious calculus class, you need to have functions as a prerequisite, and set theory preferably too. So what is the area of the region here bounded by the graph that you see here? Now, I'm not going to address question number two as much today because for that, we need further more concepts. We can see that down the line. But we'll have more tools as we go through. But the immediate goal here is to try to answer question one. And the answer to question one is the fundamental calculus concept that is called the derivative. Many of you who are watching this video, you may have already taken a calculus course, or you may be taking a calculus course this semester. So we can think of, I mentioned earlier, the circle, right? So we're going to come up with some provisional definitions. And let's see if we can talk about that. If I can put it on the screen because I had it earlier. So we came up with a provisional definition in class, in my actual calculus class. And it is that a tangent line to the graph of y equals f of x at the point a and f of a, where a is in the domain of f, is a line. We're going to have a line L that passes through those points and that does not intersect the graph at any other point. So I'm going to put this on the board and see if it shows up. Okay, this is our provisional definition here. Now, we're going to try to use this provisional definition, and let's think of a simple function, right? Let f of x and we're going to do x squared, right? If the question here is find a tangent line under the provisional definition that we have here, so we're going to find a tangent line to the graph at the point 1, 1. All right. Now, any line other than a vertical line, obviously, through point 1, 1 is going to satisfy. Remember, if you remember back from point slope and slope intercept, if you have the equation y minus 1 equals m times x minus 1, that should be a lowercase y, by the way, but so m is the slope. So that means that y is equal to mx plus parentheses 1 minus m. You want to find m such that the point that we have here, 1, 1, is the only intersection. This is very important. The only intersection of y equals x squared. And of course, y equals mx plus 1 minus m. So that means that your 2 points, x, y, which we have here is the 1, 1, is the only solution to a system. If we create a system of equations, we would have y equals x squared I'm going to bring this down so that we have more room. There we go. And we're going to use y equals mx plus and in a parentheses 1 minus m. So we have this system here. Now, if you eliminate y, right, that would give you the x squared minus mx plus m minus 1 equals 0. And you're going to see that it's, excuse me, it's a quadratic equation in x. So clearly, x is equal to 1 is a solution to this equation. We already know that. But it's going to have another solution. Remember from the theory of quadratics, when you have when your discriminant is positive, right? It's going to have another solution. So when x is equal to 1, if you want x equals 1 to be the only solution, you must have the following quadratic. You're going to have m squared minus 4 keeps capitalizing things randomly. We're going to have m squared minus 4 parentheses m minus 1 equals 0. All right, now, this, you can simplify this because if you factor or put it in a certain form, you have m minus 2 squared equals 0. If m minus 2 squared equals 0, then m is equal to 2. Now, you have to think for all the other values of m, the discriminant is positive. So there are 2 solutions. And therefore, the slope of the tangent line is m is equal to 2. And if m is equal to 2, the equation of the line is y equals 2x minus 1. And if you actually graph this, I actually graphed it and, well, created a little diagram since I know some students like diagrams and I try to be as helpful as I can. And I'm going to show you kind of what it looks like, the theory behind it, right? This is what we're talking about here. So this kind of should convince you perhaps that we did the right thing. It looks like the correct tangent line. And this all looks fine, but I mean, I think it seems like a lot of trouble to go through just to find a tangent line. And as I've said in many other videos before, don't make your life harder than it needs to be, right? You don't want to spend so much time. So another issue is that there is another line that intersects y at y equals x squared, only at the point 1, 1. And that is when the line, that is when you have x equals 1. Now, we didn't get that line in our solution here because the slope is undefined. Why is that? Because you remember our other than a vertical line qualifier that we said earlier in the, so when we started solving this in a previous video, I hope it's still up. Someone told me it wasn't, but there's a previous video on this where we actually solved a similar one. So you can see that any graph y equals f of x, the line x equals a is going to intersect the graph in only one point. And in this case, a comma f of a. And that is called the vertical, you know this if you know functions, that's called the vertical line test for graphs of functions. There is only one y value for each possible x value, in the domain. So you can, now we have to revise our provisional definition and we have to exclude vertical tangent lines. And if we do that, our definition, again, this is all provisional because we haven't done the proof. But you can have as follows. Let's see if I can put it on the, okay? This is, so a tangent line to the graph y equals f of x at the point where a is the domain of f is a line not parallel to the y-axis passing through a f of a, and it does not intersect the graph at any other point. But we have a more significant flaw, because if we look at a slightly more complicated example, what if you had a problem, let's say, that asked you, find the equation of the tangent line and we'll say to the graph of y equals, let's do x, trying to think of a good, x cubed plus x at the point 1, 2. So if you have a non-vertical line through point 1, 2, we're going to have to create an equation as usual. We have y minus 2. Remember, it's y minus y sub 1. So we could do y minus 2 equals, and the point here is 1, so we're going to do x minus 1. So we're looking for a value of m that gives only the solution that we have here, that we get a solution of 1, 2 to a system. So if we create a system, we have the first equation is y equals x cubed plus x. And our second equation would be mx plus, if we simplify, mx plus parentheses 2 minus m. So we can also set these two equations equal to each other. And that would give you x cubed plus 1 minus m. And you could do the easiest way is to just set them equal to each other. So x cubed plus 1 minus mx. And we should put that in a parentheses. And if we do plus m minus 2 equals 0. All right, now, you already know that x equals 1 is always a solution here. So you can factor the equation then, right? We can factor this as, well, the common factor would be x minus 1. So if you have x minus 1, um, we're going to do, and then from here, x squared plus x. And you also have minus, well, minus m minus 2 inside the parentheses equals zeros. So if that's the case, you need the cubic here to have no other roots. You have a cubic function here, so you can't have any other roots. So either the quadratic has the double root, x equals 1, or the quadratic has no roots. And since you want x equals 1 to be the only root of the original cubic, right? So you have a monic quadratic with double root. We have x equals 1, x squared minus 2x plus 1. But that does not match your quadratic here. So the only possibility is for the quadratic to have no root. And now you need the discriminant of the quadratic, if that's the case, to be negative. So what is the discriminant here? Well, the discriminant is 1 plus 4 parentheses m minus 2. That's going to be negative. It's going to be negative when m is equal to, or actually less than, I should say, 7 over 4. So any line with a slope that's less than 7 quarters through 0.12 intersects the graph that we have here, x cubed plus x, only at the point 1, 2. This is really a bad state of affairs, ladies and gentlemen. This is a really bad state of affairs. We have a whole range of tangent lines, and worse, none of these lines really look like good candidates for a tangent line. So they're sort of intrepid, aren't they? They're kind of being fresh. They all cross the graph, and I'm going to show you if that happens, a little diagram here. I've been improving with my diagrams because I know some of you are visual learners, and it is very important. This is very important with visual as well, so that you can see what's happening. Um, so they're all crossing the graph here. And if you think back to the original circle example that I mentioned earlier, the tangent line through a point just touches the circle, but it doesn't cross it. It doesn't cross that circle. So we'd like that property to be true of more general tangents to graphs. I mean, I think most of us would like that, right? We don't like intrusions. I certainly don't like intrusions. And you can see a little bit of what's really going on here. If you look at the value of m that makes your quadratic also have the root, right? We're talking about x equals 1. We need to talk about it as a root. If you plug in x equals 1, you would get something to equal to 0, so m equals 4. But if you draw the line with having a slope of 4, then you get a picture that looks as follows. This is what it looks like. So the number, we're being too vague. We're being too vague. I don't like that. And mathematicians certainly don't like that in general. So we need to define precisely what a tangent line is. But this is not easy. We're seeing that it's not a simple task. However, what is easy to define is a secant line. And a secant line, we said, is any line that intersects the graph in at least two distinct points, as you have here. From geometry, you might remember that. So if they give you 2 points, and of course the A cannot equal B, right? You have a secant line, unless it's a line that is a linear polynomial or a constant. That's a whole different matter. We expect that there's going to be infinitely many secant lines through P. However, but if Q is very close to P, then the secant line is very close to what we want to be the tangent line at P. In fact, as Q approaches P, then you have the secant line approaches the tangent line. And I'm going to show you a little diagram also of that. It's kind of how you see it intuitively. And that sounds, we're talking about approaches here. Doesn't that sound like the job for a limit in calculus? So this is sort of the approach. In my next video, we're actually going to go through the formal definition. In my next calculus video, I should say, because I create many subjects. But in my next calculus video, we're going to create the definition, the real definition of the derivative. We're going to take this informal discussion and try to make it rigorous, because we care about rigor. And, here at City Tutoring, that's what we're concerned with. So if this video was useful, please like it. Please subscribe to the channel. As you can see, I have already improved with the equipment. I hope the sound quality is better. And we're ready to just continue working for you and continue to share the beauty of math. From a rigorous perspective, though, this is, a lot. If you use some of the calculus textbooks out there, like what do they use now? Larson, Stewart. I'm not a fan, and I would never use that in my classroom. But I understand why so many instructors would be using Cengage. A lot of them are just trapped in the Cengage web. But we don't take that approach here at City Tutoring. I certainly don't take that approach. We are pure mathematicians, and we are concerned with the beauty of math, but also a little bit more rigorous standards of math. If you are interested in a textbook that I would recommend, a calculus textbook, some of you have asked me, I would go with Spivak Calculus. If you don't find it, I mean, I think it's readily available. But if for whatever reason you're in a location where perhaps you could try Apostol, Apostol. That's also a fairly good book. He was Apostle was a Greek, I believe he was Greek or Greek American, and he writes his book from a more from an engineering perspective, which I'm not a fan of, but the exercises in Apostle are top notch. So I would not discard the book just because he was an engineer. Um, Hopefully this video was helpful to you. Please let me know in the comments if it was. If it was not, let me know also. We like honesty. So I wish you a good weekend here from Virginia, and we'll be in touch. Thank you.